All right, thank you, Daryl, for that introduction. And hi, everyone, and welcome. I hope everyone is having a good day today, and I hope to keep that going for you with this OpenJ9 Vitality Talk. My name is, as Daryl mentioned, Jonathan Newman, and I'm here with Shubham Verma, and we're excited to be here to talk to you about large array optimization for OpenJ9 balanced GC. A quick note that the information contained in this presentation is just for information purposes. A quick outline for today. So I will give a brief introduction. Then I'll talk about balanced GC and the balanced GC algorithm and some key concepts there. We'll then go into off-heap memory management from a GC perspective. Then we'll talk about off-heap memory management from a JIT perspective. We'll do a quick summary and then finish with some questions. A little bit about myself. I'm an OpenJ9 VM GC developer at IBM. I've studied computer systems engineering at Carleton University. I'm most interested in machine learning and AI, compilers as well, and of course, garbage collection. And a little trivia about myself is I'm actually from a family of 13 with 2 wonderful parents and 10 siblings. So a little bit about Shubham. He's an OpenJ9 JIT developer at IBM. He studied computer engineering at the University of Waterloo, and he's most interested in compilers, psychology, and systems. A little trivia about him is he is an aspiring overlander, which is very cool. Quick note about Eclipse OpenJ9. So the project that we both work on, which is a as most are familiar, a high performance scalable Java virtual machine implementation that's fully compliant with the JVM spec. So I'm sure many of you are familiar with garbage collection, but to set a baseline of understanding, garbage collection, or GC, is a form of automatic memory management, where so the garbage collector attempts to reclaim memory occupied by objects that are no longer in use by the application. So I'm sure many of you are also familiar with programming languages such as C and C++, where the programmer needs to manually reclaim memory to avoid memory leaks through malloc and free or new and delete operations. With garbage collection, there's 3 fundamental tasks that I'll say will fall under the umbrella of garbage collection. So 1 is the allocation of memory, 2, the identification of live data, and 3, the reclamation of garbage. So there are some benefits that come along with garbage collection, 1 being the automatic memory management. So it frees the programmer from memory management decisions. 2, it also helps reduce certain categories of bugs, such as dangling pointers, double freeze, and various types of memory leaks. On the negative side, it's going to require additional resources. So GC algorithms generally require additional CPU usage or physical memory for data structures. It's going to cause unpredictable pauses. So most GC implementations cause stop the world or SDW pauses. And then it's going to also likely introduce runtime costs. So the GC algorithm may require a read and write berry overhead and getting all threads to a safe point and then letting them execute again after a GC can take time. And lastly, the application really has little control of when memory is reclaimed. So now today we'll focus on the balanced GC collector. So it is a region-based generational collector. And so if we break that down, region-based, so the OpenJ9 Balanced heap is logically divided into regions, and the regions are GC'd as needed. And then if we break down the generational side of this, generational garbage collection schemes, these are based on the empirical observation that most objects die young. So in generational garbage collection, 2 or more allocation regions or generations are separate based on our created generation that is going to be regularly collected. And when a generation is full, the objects that are still referenced from older generations are copied into the next oldest generation. And occasionally a full scan is performed, although that is trying to avoid that. So with balance, this is also going to provide a significant reduction in max GC stop the world pause times. It's going to introduce a write barrier to track inter-region references, and it's also going to result in incremental heap defragmentation. So balanced GC is focused on balancing the time spent in collections while still providing good throughput. So balance tries to pick regions with a high ROI or the collection set, and then has a goal of having no global collection, meaning the entire heap needs to be collected. So we're going to set partial garbage collection time goals, and we're going to try to pick regions to meet these PGC or partial garbage collection time goals. And these the new regions where we're allocating data, these are always included in the collection set. So with balanced heap, the heap is divided into a fixed number of regions. Region size is always a power of 2. And we're going to attempt to have between 1,000 to 2,000 regions, meaning a bigger heap doesn't mean a higher region count, but will lead to a bigger region sizes. So with the balanced heap, we're also going to allocate from Eden or new regions. So Eden can be any set of completely free region. And we're going to attempt to pick regions from each NUMA node. So objects in a single region share characteristics such as being of a similar age. So each region has its own age. And as I mentioned, Eden or new regions are always included in the next GC cycle. So with balanced heap, no non-array object can be larger than a region. So if the object size is greater than the region size, we're going to throw an out of memory error. And this is quite rare. And that's because even with, let's say you had a tiny 16 megabyte heap, we will have a minimum region size of 8 kilobytes. And with 8 kilobyte regions, even if you're running with full references, so 8 bytes per reference, we would only throw an out of memory error if the object had over 1,000 reference fields. So this is why in practice, we're not really worried about this so much about this case. Now, large arrays, on the other hand, which are arrays that are with data larger than the size of a region, this does occur often in practice and in balance. This is handled by allocating them as what we call arraylets, which I'll elaborate on more very shortly. So arrays, and then arrays less than the size of a region, these are allocated just like normal arrays because they can fit within a single region. So with arraylets, large arrays, these are large arrays that cannot fit into a single region. And arrays, the array is created from a construct comprising of an arraylet spine and one or more arraylet leaves. So an arraylet spine is allocated like a normal object, and each leaf consumes an entire region. And so these arraylet leaves, these are the region-sized chunks of data of the array. So arraylets, they were introduced so that arrays were more cleverly stored in the heap for region-based collection policies. Another key benefit of arraylets beyond reducing probability of stop the world global GCs is that if an array survives a local GC, only the spine is copied, while leaves stay where they are, which reduces GC overhead. So looking at arraylets visually, so if you look at a picture of this region-based heap, regions in the heap are these are squares, and blue represents arraylet leaves, green represents an arraylet spine, and the rest are empty regions. So looking at the arraylet spine, we'll see the header that will store information such as the class, the length of the array, and data references or arrayoids. You'll often hear me refer to them as. These arrayoids are pointers to the arraylet leaves, which are region-sized chunks of the array data.
Joe, do you need to advance the slide?
Not quite yet. I could actually, if yeah, I could. Well, it will be marked on the next slide. So as I mentioned, so these are the region-sized chunks of data for the array. So now expanding that a little bit more. So we've now we introduced you'll now introduce the box, which will depict regular objects. You'll see again the arraylet spine, will have the header, and followed by the arrayoids that you'll see there that are now labeled in lieu of the data reference label that was there on the previous slide. So expanding further on the arraylet leaves, we'll see that this simply contains the array data in a region-sized chunk, and arrayoids can be used to access specific elements of the array. So given a request for a specific array index, the array pointer is calculated, and as well as the index into the array pointer, and with this information, we can access that specific element. So some drawbacks of arraylets. So various JIT optimizations require a contiguous view of an array. Some APIs, so for example, Java native interface or JNI critical APIs require a contiguous view of the array. And so JNI critical, this is used when the programmer wants direct addressability of the object. And so JNI allows Java programs to call native code, C, C++ code, giving more flexibility to the program and functions that it can use. So in order to do so, JNI critical, it'll require a contiguous representation of the array. And how does it do that? Well, in the case of contiguous arrays shorter than a region, it can just use the array. However, in the case of discontiguous arrays, so arraylets, JNI critical copies element by element to a temporary array, so that JNI critical has this contiguous view of the array. And when it's done, it copies all elements back, again, element by element. And yes, that sounds expensive, and it most certainly is. So arraylets are considered to be the primary reason balanced throughput is slower than GenCon, which is the default GC policy with OpenJ9. So looking now at off-heap allocation for large arrays, so small arrays with this new scheme, small arrays are going to be allocated entirely on heap, as they've always been. But this off-heap allocation for large arrays is going to provide a contiguous view of array data to the JIT optimizer and other APIs requiring this representation, and will eliminate the need for arraylet. So it takes advantage of the vast virtual memory space provided by 64-bit CPU architectures. As with off-heap, in order to provide a contiguous view of these large arrays, the 64-bit address space, which allows us to be able to theoretically reference over 17 billion gigabytes of data, meaning the concept of wasting address space for off-heap allocations is not an issue compared to the 4 gigabytes of addressability offered by 32-bit architectures. And lastly, there is now a new array header field called data address, which is now added to access array elements. So with off-heap allocation for large arrays, if we look first at GenCon, so we'll talk about some of the benefits of off-heap, and let's see how we'll see now how it fits into the puzzle visually. So first, let's look at GenCon, which does not benefit from off-heap, as the heap layout in GenCon is essentially a 2-region heap. So it's impossible to have an array larger than a region, or GenCon doesn't allow arrays larger than a region, and for this reason, data can always be stored contiguously after the object header. Now, let's look at balanced and how it exists currently. So without off-heap allocation for large objects, for small arrays, if you look at contiguous shape for the balanced layout for small arrays, you'll have the header, so the class and the length, followed by the array element directly after this header. But for large arrays, so this contiguous shape with the arraylets that we've discussed, we'll have the class, the header, so the class and the length, and this arraylet spine, which is going to have those arrayoids, as mentioned, which are going to be pointers to your arraylet leaves, which are going to be holding those region-sized chunks of data of the array. Now let's introduce balanced with off-heap. So this is going to remove the need for arraylets, as data for large arrays can now be stored contiguously. So for small arrays, we have they're going to be on heap, and the layout will have the header, so the class, the length, and this new data address field. And as mentioned, the point of the data address field is to point to where the data of this array is allocated. And in this case, for small arrays, the data is stored right after the header. So this data address pointer is just going to be pointing right after the header. Now, for discontinuous arrays, or previously discontiguous on balanced, this layout will have that, so that this header will have the class, the length, and the data address field, which is going to be pointing to this secondary off heap that will be managed specifically for the allocation of data for the arrays. So looking at the overall props object, but it's an object, and so the class will have information as a class, the size, and this the object pointer or data address pointer, which will point to now this off heap. You can see it's going to be storing contiguously the data for this large array. It allows us to be able to have a contiguous representation of this data. So expanding this, we have this proxy object that's with array data stored off heap and pointed to by the data address field of the proxy object. So this off heap will be managed using a linked list of free list entries for off heap. We'll have an off heap data pool that will hold an off heap pool entry for each off heap allocated object, and a hash table as well that will be used to map the data address of each off heap allocated object to the respective proxy object address residing in heap. So these are some of the core structures needed to manage this new off-heap scheme. Now, if an object moves in heap, we can use the data pointer as the key for the entry in the off-heap management hash table that must be updated in order to update the proxy object pointer. So, and also if an object dies and that had data stored off-heap, the data pointer is all the information we need to clear all remnants of this object in the off-heap managing structure and off-heap. So now that we've talked a little bit about in-heap and off-heap and how proxy objects are stored in heap and the data for the large arrays of these proxy or spine objects is stored off-heap, let's take a look at some high-level flowcharts of an off-heap allocation. All right, so first, let's say we received a request to allocate an indexable object. We need to know, is the data size of the indexable object larger than a region? So no, then we allocate the array normally as we would for a small array and set the, so if off-heap is enabled, then we'll set the data address pointer to point directly after the array header in heap, as the small array can have its data stored contiguously. And so let's say the answer is, yes. So the indexable object is larger than a region. Then, okay, we're dealing with a large array. Then we need to ask, is off-heap enabled, and are we running on a 64-bit CPU architecture, as off-heap allocation hinges on the vast virtual memory space of 64-bit addressing. So let's say the answer is no, then we allocate arraylet leaves, or so no meaning off-heap is enabled and we're not running on a 64-bit CPU architecture. Then we're going to allocate arraylet leaves for the array data as what's currently done in balanced GC and in OpenJ9 before the existence of off-heap allocation for a large array. So let's say yes, we are running with off-heap enabled and 64-bit CPU architecture. We're going to allocate the data for the large indexable object off-heap. So on this next slide, we'll look at a high-level flowchart of how we'll allocate the data for the large indexable object off-heap. So one of the first steps for an off-heap data allocation is to reserve leaves for the array data and to decommit memory for these leaves. So in order to allocate memory at off-heap, we need to decommit these leaves in heap. So this is going to disable the region for read and write from other threads, since the read and write will be done through the contiguous representation of the data. And so this decommit is done because the Java heap has a limit on committed memory, and we can't surpass that, as if we did, we wouldn't really be complying with the application's specified max heap usage, as other threads would then be able to, as other threads would then be able to allocate to these regions, and off-heap allocations would not be correctly accounted for and result in the application committing more memory than allowed by its max heap specification. So once this large array object dies and is reclaimed by GC through a new scan that's been introduced at the end of a GC that scans the heap for dead spine objects with data allocated off heap, we recommit those same leaf regions, and the original leaves are mapped back to their original state, and these regions can now be used again to allocate new objects. So next, we're going to enter the off-heap mutex, which is, this must be done before modifying off-heap managing data structures, since many threads will be trying to modify these, could be trying to modify these structures. And yeah, we need a monitor to ensure the integrity of the off-heap data. And since there aren't lots, and most applications there isn't a high demand from many threads often at the same time for off-heap allocation, this mutex isn't in very high contention, so there isn't too much waiting that takes place. So from there, we look in the off-heap relist pool to find a suitable location to accommodate the array data size that's being requested. Since at the level limits page sizes, we need this data size requested to the page set. So we get the memory, full memory or off-heap, and let OS know that we are using this memory off-heap. Then we zero this memory, which only needs to be done explicitly on the platforms that don't automatically zero memory on memory commit, as several platforms do this automatically. So after this, we create an off-heap data entry in the hash table that manages off-heap allocated objects. So this entry will contain the data address pointer, the size of the data stored, and the proxy object pointer, which is the in-heap spine object that owns, quote unquote, this data. So this allows us to map this off-heap data address pointer to the heap proxy object that resides in heap. And so finally, in the indexable object header for this newly allocated indexable object, we're going to set the data address pointer to the address returned by the off-heap allocation function. So I hope you now have a better understanding of the high-level process for an off-heap allocation. So with off-heap allocation for larger arrays, any platform that supports virtual memory can benefit. It unburdens in heap from large object allocation. Off-heap will never need to be compacted. And it's going to provide a contiguous view of array data to the JIT optimizer and other APIs requiring this representation. Now on the con side, so whenever we commit memory at off-heap, we must decommit memory at in-heap and vice versa. So whenever we commit memory at off-heap, so as mentioned a few slides ago, one of the first steps of an off-heap allocation data is going to be to reserve leaves for the array data and to decommit the memory for these leaves. So in order to allocate memory at off-heap, we decommit these leaves in heap, which will disable the region for reads and writes from other threads, since reads and writes will be done through the contiguous representation of the data. So this decommit is done to, just to reiterate, it's done to, because Java heap has a limit on committed memory and we cannot surpass that. And if we did, we would not be complying with the application's specified max heap usage, as other threads would then continue to allocate to these regions, and off-heap allocations would not really be correctly accounted for and result in an application committing more memory than allowed by its max heap specification. So once this large array object dies, it's reclaimed by GC through a new scan. At the end of the GC, that is going to scan the heap for dead spine objects, or we're going to iterate regions. We're going to iterate regions, but we're going to essentially, we'll scan for dead spine objects with data allocated off heap. we'll recommit those leaf regions, and the original leaves are mapped back to their original state. And these regions can now be used again to allocate new objects. So it should be mentioned that through that though there's some overhead described, it is small, and it's really not a cause for concern, but still it may be investigated in the future to find out if there is a way around it. And then secondly, there is now one extra level of indirection to access array data. So although when running with the JIT compiler, this which will always be the case in practice, there are clever operations we can do so that this cost for this one extra level of indirection to access array data is minimized. So now that we've talked about off-heap allocation from a GC perspective, I'll now be passing it over to Shubham, who will be talking about off-heap from a JIT perspective and overall a JIT and performance actually perspective. Thanks, Shubham, and over to you.
You're on mute, Shubham.
Hi, Shubham. I think you might be on mute.
Sorry. Thank you. Thank you, John, for that wonderful GC perspective. And hello, everyone. So in the next few slides, I'm going to be talking about the benefits of off-heap management from the JIT perspective. So to start off, first one is array access is unified for both large and small arrays. Just to recap what John had previously said. So in the balanced world, the way things are now, large arrays are allocated using arraylets, whereas small arrays are allocated contiguously, both of them on heap. Because of this dual layout, the JIT cannot make any assumptions about the location of array elements because for the contiguous arrays, the data will lie right after the header. However, that cannot be guaranteed for large arrays. And as a result, we must use special IL instruction called spine check for each array access. So to compare with off-heap, both small and large arrays will be allocated contiguously. Small arrays will be contiguous on heap, whereas large arrays contiguous off heap. We'll have a new field in the data array header called data address pointer, which will always be tracking the data portion of the arrays, regardless of the size. So the benefit of this is that we don't need to do any runtime checks to get to the array elements. This allows JIT to essentially do array access without any runtime checks, and this in a unified manner for both array sizes. So now this leads continue on to our next benefit, which is the optimizations. So previously, for balance, since we were using arraylets, special handling was needed. This generally made manipulating array access IL tricky. And up until now, the best solution has been to simply disable those optimizations. However, now that we have array access, we had unified array access for both, regardless of their sizes. The optimizations which were previously exclusive to the world where arrays were only contiguous, those optimizations could be enabled for balance running with off-heap. So some of those optimizations include vector API expansion, idiom recognition, and unsafe atomic operations. So now on this slide, I'll be talking about the IL trees that are generated for both array access with arraylets and with off-heap. So first off, for arraylets, so spine check here, this is the special instruction that we need to generate or we need to use when doing the array access in the arraylets world. So like the name suggests, a spine check, it looks at the array and checks if the array has a spine or if it's using arraylets or not. And depending on that, it will later on take two different code paths. I will expand on those code paths in the next slide. And for comparison, these are the IO trees that are generated for array access for offheap. So as you can see, there's no special instructions are needed. We simply load the data address pointer, which is from the array header. So that's at this offset, and use that for our calculations. So that kind of takes on to our difference between the two. For spline checks, we use the array object as the base of our calculations to get to the element. However, for offheap, we use the data address pointer as base of our calculations to get to the array element. So now, on this slide, I'll be talking about the control flow for array access with arraylets and with offheap. This is really where we can observe the difference and really appreciate the benefit of having offheap enabled. So first off, this is the control flow for array access with arraylets. So this is what the spline check translates to. We must first check if the array has spines. So that is done by reading the size field of the array. So the way it's implemented is that the size field is overloaded. So if the size field of contiguous headers, so at that offset, if the size field is 0, that means it's a discontiguous array. However, if it's a contiguous array, or that value will be a non-zero value. So if the value is non-zero, we're dealing with contiguous arrays. We don't need to do anything. We simply add the array object, header size, and the offsets in bytes. However, if the array it has been allocated using arraylets, we must jump to this out-of-line code sequence where we would calculate first we need to calculate the address of the arraylets leaf that the element is in, then calculate the address of the offset for the element with respect to that leaf, and then we use that to calculate the address of the element, which will be returned back. In comparison, here is the control flow for doing array access with offheap. As you can see, it's very simple, no runtime checks needed. To calculate the address of the element, read the data address field from the array header, and add that to the offset for the element in bytes, and that's it. So for arraylets, we need at least 9 instructions for reading an element in a discontiguous array. So that's 1 instruction to compare, one instruction to check if the array has a spine, 2 to jump back, 2 to jump back and forth from out-of-line code sequence and inline code sequence, and 6 of those to actually calculate and read the element that we want. These extra instructions and the jumps add additional. It increases the register pressure because additional intermediate values must be preserved and updated when running the application. In comparison to offheap, there's just two load movements or load instructions, one for data address field and another to get to to read the element address. So the benefit of being less instructions, less register pressure, and no jumps. So now that we have contiguous, we have unified array access, here are some of the optimizations that can now be enabled, or the optimization that can leverage the offheap technology. So first one being vector API expansion, scalarization or vectorization of recognized vector API calls such as load or store to an array. The next one being idiom recognition. So array copy, array compare, and array translate. Next one being escape analysis. So previously, stack allocation was supported only for non-array objects. However, non-array objects in the balanced world. So with the offheap now, that can be expanded to arrays as well. Unsafe array operations such as array get and add, get and set, compare and swap. String function accelerations. So this includes string case conversions, string.indexOf, integer to char conversions, so integer.getChars, long.getChars. And finally, something new, something we have recently accelerated is CRC32 and CRC32C. So all of these optimizations can now be turned on because of the OFI technology. So now, this is what that looks like in terms of throughput. So first one here is what some performance numbers that we calculated for Liberty Daytrader 7 on Linux X compared to baseline GenCon. Balance GC is regressed by 19%. With OFI technology enabled, the gap between balance GC and GenCon is reduced to just 5%. This means with OFI, that is with just this array is disabled, or arraylet's gone, we're able to recover 14% of the performance. Now, here's another Java business logic benchmark where we gathered performance numbers for. So this benchmark is models a typical store workload, which includes online transaction, in-person transactions involving POS terminals and cache. Compared to baseline GenCon, balance GC is regressed by 37%. With OFI technology enabled, the gap between balance GC and GenCon is reduced to just 9%, meaning we're able to recover 28% of the performance. So now on to some of the challenges that we encountered during our design and testing phase of this project. So before we get started, a bit of a background here. So during our initial prototyping phase, we wanted to mark the data address pointer, so this the node N5N, that as internal pointer. The reasoning behind there was this is if there happens to be GC between between uses of this data address pointer and the array gets moved, we want to make sure that we always pointing to the correct array. So instead of coming up with a new infrastructure, we decided to piggyback on the existing infrastructure to ensure that GC that pointer gets updated after GC. So now the first challenge that we faced was there's a cap on internal pointers, so there's 128. With us trying to mark each data address pointer as internal pointer, we ran into the issue of running out of the quota for internal pointers. To solve this, we decided to cache data address pointer loads for the same arrays. So that led us to our next challenge, where so this is a quick visualization. So what we decided was we would cache it. So if you see element load for the same array, we would we should get to the first one, cache it, and then reuse it. However, the problem here was that we needed to follow we couldn't rely on a flow order, meaning that we cannot assume that it will be okay to reuse it at the next block. We needed to use contextual order to maintain functional correctness. So the solution there was that we do need to mark data address pointer as an internal pointer, because at the time, or at least at that time, it wasn't being commented across GC cycles. So there's no need to worry about the array being moved and us having to figure out where to get to a new location. And the other benefit was, so here if you can see the snippet, the parent, the AL add, is already marked as internal pointer. So even if the array gets moved, this will get updated appropriately. Now, to our next challenge that we face. So with the addition of data address field, it was enabled by default in all GC policies. It included GenCon, which would not benefit from it. So when it was enabled, even in GenCon, we had to spend GC CPU cycles populating the field, and during our benchmarks, this translated to about 3% regression in GenCon compared to baseline GenCon. However, we were able to gain this performance back with our dual indexable header shape. So more on that on my next slide here. So as I previously mentioned, data address field was enabled by default for all GC policies, regardless of if the GC policy in use would benefit from it or not. With dual indexable header shape, we are able to toggle the field based on need, meaning if the GC policy would stands to benefit. So for example, for balance, we would toggle it on. And if it doesn't, then we will just leave it off. This check happens right before JIT is initialized, so GC does some runtime checks to determine this. This allows us to recover all the performance that we lost when we had initially enabled data address field by default. So the result was no more regression, no more throughput regression in GenCon due to data address field. So now, as part of the offbeat work, we also introduced some new IL APIs regarding array access to reduce some technical debt and consolidate the mechanism and the logic in easy to maintain and usable location. So here are some of those APIs. The first one being array address tree. So this takes in a base array and the offset node and generates the trees based on it will check if the off heap is enabled. It will do a data address load, and if not, then add the data array header size to the offset node to get to the element. Next one being data address load. So if an op needs to simply go in and replace the offset node or the header size with data address load, this is something that could be useful there. And there's another API to generate the offset trees. And here are the two additional APIs that were created. So now that the tree layout will be different than when it was before. Previously, anytime you encountered an element access, so you would see add with the array object as the first child, and the second child will be the offset. So now that that's changed, we would need to update the logic behind finding the index node and the base node. So these APIs would help with that. Now, implementation and status and feature work. So first one, integration of the dual header shape into the existing offbeat implementation. So the dual indexable header shape has been, the GC part has been checked in, and the JIT part is under review. Once those are checked in, we will need to pull those changes into our offbeat work and investigate if there are any failures. Now, so far, most of the testing has been done on X. Our next goal is to expand the offbeat technology to be fully functional on additional platforms, so IBM Z, ART64, and Power. And so the target release date in all Java versions is Java 21 for the offbeat technology. So to summarize, offbeat management unburdens in heap from large object allocations. Offbeat management allows us to unify array access for small and large arrays. It also allows us to close the performance gap between GenCon and balanced GC policies by a significant margin. And thank you, folks, for listening. Do you guys have any questions?
Thanks for the talk, guys. It looks like it's some fairly promising work to recoup some of the performance that we lost when the runtime performance that we lost with balance. So looks good. One question that that I have is on the I guess on the serviceability side of this. Right now, the heap information is listed in one section in the Java core. how do you account for the memory? How do you account for the off-heap memory that gets allocated? Will that be reported in the Java core with the rest of the heap information, or how is that handled?
So currently, the off-heap, at least the overall total for off-heap allocation and some basic information about it isn't is reported in through verbose GC logging. So and there's also various levels of tracing you can have running with off-heap. As far as the core goes, that isn't there wouldn't be any. I don't believe there would be any reports of off-heap, at least not currently.
So these are just considered to be memory segments that are going to be attributed to the VM? Is that how they would be reported then?
I guess I'm not sure if that has been a topic, I guess, of discussion within the course. So I don't think there is a I don't think there would be a way to have them have off-heap allocations denoted currently within the course.
We haven't done anything explicitly about that. If that, I don't know, maybe Dmitry knows, it maybe show up under metastructure section of a GC somehow implicitly, but we haven't. That's a good question. I guess we should do something about that. But anyway, the kind of priority was deliver the core feature and let it soak and test. And while we're doing that, we would certainly address some of the, I guess, serviceability issues in a kind of in parallel.
All right, sure. Other questions?
I have a question. So it's very simple question, but like I missed starting 10 slides or 15 slides, but I'm working on arraylets as well, but like so I see there's a off heap. Is there a difference here? Because I saw some of the slides were trying to show that there is a difference here of heap and they're using arraylet. So so the memory that's been used by off heap, is this the out of the this is a memory that is out of the memory that JVM usually use? That JVM have given a certain chunk of memory, right? So is that off heap is literally outside of the JVM? So can you clarify that? And then is arraylet is when arraylet been used, is this the same thing as off heap or is it different things?
So this would be different things. So off-heap would be replacing the use the need for arraylets. So when it comes to we will still, as I mentioned, we will still reserve arraylet leaves for allocations to ensure that we're not over committing memory. But the off-heap is there to remove the need for arraylet leaves. So this yes, if I does that answer the question?
Yes, that's
Or
certainly
is there
that's certainly I get answer for one part of it. The second part of it's there. So is this off heap memory is out of the JVM memory? Like where is that? Where we allocating it? When you say that it is out of it says off heap, right? So it's not in the heap. So heap usually used in the JVM, right? And then after that, is this the memory object that you're allocating there with the off heap? Is this the out of the JVM? Where is and then how? So that's, can you clarify that as well?
So it's outside of the primary in heap. that's allocated and initialized when initialized at JVM startup.
I have a follow-up question on that then. So what if other applications are busy using rest of the memory outside of the JVM? So how will that throw an error?
No, no, it will not. It won't have in that way. It won't have an impact on other applications.
Okay, makes sense. Okay, thank you. I have couple of more questions if others don't have it, I guess.
Go ahead.
Yeah,
Okay.
yeah, for sure.
So one of them is on slide 17, I think, where there was a diagram of arraylet. So I want to know the difference here, or if it's the same thing. The arraylet data, if you look at there, the red boxes there, right? Can you give me an idea? Like, is this arraylet data is this the same as the arrows, or is it a different thing?
Oh, I see. So the arrayoids are going to be the pointers to your arraylet leaves, which are so when you allocate arraylets, the overall data is broken down into region sizes. So we're allocating these arraylet leaves are going to be region sized chunks of data. So these arraylet data that you see so this arraylet data wouldn't actually be adjacent to the header as you see it depicted. So that's as you see it depicted in the diagram. I'm not sure if it's possible to share. I guess I can steal back the sharing so that you can see what I'm talking to. Just one moment.
Yeah, it just created a confusion when I was looking at the diagram, right? Because the coloring, because when we look at the inside the leaf, right, it's also a data, right? So, so and then we look at it here, the array data in the same sequential manner, right after the header and then arrowhead references, right? So I was trying to make sure that if it is not the same thing because of the coloring effect.
Yes, no, you're correct. I do see the the confusion. So if like how it's how it's shown on this diagram, at least in the bottom, that's if you were to actually put those leaves adjacent to the header. So in reality, these arrayoid pointers, these leaves, so that where all the data is stored, as you can see in the top left corner where we actually expand an arraylet leaf, this won't actually be adjacent to the header as you see it denoted in the bottom half. I do see the confusion there. So these arrayoid pointers would be pointing to these arraylet leaves all over throughout the heap. And in those arraylet leaves, as you see expanded in the top left corner, are going to be all your array elements for that leaf. I hope that clarifies it.
Yeah, sounds good. And so I see there was on slide 33, what was mentioned that that optimization was disabled. I think when Shubham was also talking on that time was there was what was the reason for disabling the optimization? Like it says due to an arraylets, right? So is there a specific reason it was disabled before?
The JIT disabled it because it was those optimizations expected a contiguous view of the data. So for in arraylets, data is spread out using all over the heap using arraylets, and that was the primary reason why we disabled those optimizations.
Okay, I see. Thank you. Yeah, I think that's all I have for right now, unless I come up with more questions. Thank you.
No problem.
Any other questions? Last call.
Just a very quick one. So is the code available right now for the off heap in the OpenJ9 commit? So like if I want to take a look at it, is it possible to take a look at it, or we have to just wait until the final commits or all the push is done?
So it's not quite it's not available yet on like, as in it hasn't been merged yet into master. It would be all in the code that would be in local branches. Although if you did want to yeah, I guess if you did want to reach out though directly, I could share some of these local branches with you.
And
When you
same
say
for
local, John, you
code.
mean they're in your own branch. They're in your own branch within the public GitHub.
That's correct.
Yeah.
That's correct.
So it is public. It's just within, not merged into the project yet.
Okay, so
That's
okay,
correct.
I
Thanks for
see.
clarifying.
So
Yeah.
I can just go to the commit, oh sorry, the branch, and I can take a look at it. Okay, makes sense. So the reason I asked this question because I'm working on another project, Microjet, and I was using a arraylet whenever there is a large array comes. But now I see there is another option of like off heap. So was gonna look at it like how does that make a difference? So this is the reason I asked for, if there's available, I can take a look. Thank you. That's all I had.
Okay. Okay. Excellent.
Okay, last call for questions.
Were there any performance benchmarks that are run on this optimization yet?
Yes, so we ran Liberty Data 7 and an in-house benchmark. So I believe that's on slide 43 and 44. John, if you could.
Okay, okay, yeah, thanks.
So that's Liberty and the benchmark.
Mhm. Yeah, thanks.
Okay. Well, if there are no other questions, thank you, John and Shubham, for taking us through this, and we look forward to getting this into the code base later on this year. Thank you, everyone, for attending, and we'll see you at the next one. Thank you. Bye.
Thank you. Bye.